Yeah, that's what I was just saying a little bit before in the previous session, that when you're talking about the square of the angular momentum for a human scale object, the angular momentum is so large that the eigenvalue little l times little l plus 1 itself has to be very large, and hence little l is very large, and hence the number of orientations of the component, LZ, is there are 2l plus 1 of them. There's so many of those that then the difference in the angle between each orientation becomes so tiny it's effectively continuous. So what I was just saying before. Now, the choice of which component, we chose LZ because its differential operator was the simplest. It was just d value phi compared to the others. But we could have chosen any one of the other two, like Lx or Ly, to find the eigenfunctions. Now remember, now Lz commutes with L squared, but so does Lx. Lx commutes with L squared, so Ly also commutes with L squared. So we could have chosen any pair L squared Lz, or L squared Lx, or L squared Ly. Okay. So so now Lz and Lx do not commute. Okay, so you can't measure both of them to infinite accuracy simultaneously. Their commutator is non-zero. Okay? So these two, and similarly Lz does not commute with Ly. So so you do choose this pair. So you set up an experimental arrangement that measures the component of the angular momentum along the z-axis. So that means you don't know what the component is. There's an uncertainty along the x-axis or the y-axis. And if you chose, for example, if the pair of operators you chose were L squared and Lx, well then you would have uncertainty in the angular momentum component along the z-axis and the y-axis and so forth. Right? So so in a sense, your choice of the orientation will influence what happens experimentally, the results that you get from the experiment. So there's a much more intimate link in quantum mechanics, and this is controversial, in the so-called reality, like quantum reality, the reality that you observe, the way things behave, depends on your experimental setup. Now that was a point made rather strongly by Niels Bohr, who said there's a much more intimate relationship between the observer, the human being who does the observing, and the physical reality as measured than there is in classical mechanics. Now, this is the sort of thing the philosophers of science, philosophers of quantum mechanics, really like talking about, and I'm only just touching on it now. But what you choose to observe has a certain influence in a subtle way on the outcome of your observations. So if you're choosing to measure the z component, you will get definite values for the z component, but you won't know what Ly or Lz x are. But if you choose to measure Lx, well then this becomes fuzzy, and so does this, and so on. So, more food for thought on the philosophical side. Okay, now moving on a bit. You may remember from previous lecture, I introduced the notion of using matrices for doing quantum mechanics, saying that in chapter 7, which is now this chapter, that using a matrix representation was actually very convenient for quantum mechanics and angular momentum, and particularly we'll get onto it next few sessions, on the notion of spin. But so now we sort of start talking about matrices. Now, previous lecture lecture 6, chapter 6, we said there's a very close link between Hermitian operators and Hermitian matrices. Okay? Now, can you remember the definition of Hermitian matrix? You take a matrix M and you conjugate it, so all the terms with an I, square root minus 1, they all become minus I, and you transpose it, TR, transpose. Remember, transpose means turn the rows into columns and the columns into rows. So, trying to remember how to do that. So if my hand represents the matrix, and these are the rows, then you turn them into columns, and the columns get turned into rows. That's transposing it, the matrix. So if you start with a matrix M and you conjugate it and transpose it, if what you get, the result, this, if that's equal to what you started with, M, then that matrix, by definition, is a Hermitian matrix. Okay? And the link between a matrix, or Hermitian matrix, and a Hermitian operator is this. Okay? So the bracket here, these terms here, these functions, they're eigenfunctions of your Hermitian operator A hat. Okay, and this is one element, one of well, let's say M and little n. Let's say they range between 1 and big N. Okay, so this is one element of a big N times big N. In other words, square matrix. Right. So this is one element of a square matrix, and that element is this. So now remember, it's an operator, it's Hermitian, so if we want, we could put this A here. We could move it to the left of phi M. Okay. Now, because of the, whether the A can be on the right-hand side in the ket or on the left-hand side in the bra, doesn't really matter. So remember the notation from earlier lectures. We could put like a second vertical bar here, and so instead of having a bra ket, we could have like a bra operator ket. Okay, so that's the link between a Hermitian operator and a Hermitian matrix. Well, it's just one element of a square matrix. Okay, defined by this. Now, you can do quantum mechanics using matrices of this sort, and they're equivalent. So you can use Hermitian operators and their eigenfunctions. That's the way we've been using mostly, pretty well exclusively, up to this point in this whole quantum mechanics course. We've been using this operator eigenfunction approach, but you can quite equivalently use the matrix approach. So all the algebra and logic's the same. They're equivalent. And historically, I've mentioned this a few times before, quantum mechanics, modern quantum mechanics that came out of the 1920s, the revolution started by Heisenberg and then Schrödinger. They're the two main formalisms, and Heisenberg was about a year ahead of Schrödinger. And Heisenberg's approach was the matrix approach. And then along comes Schrödinger, influenced by de Broglie, the Frenchman, de Broglie's ideas, and created wave mechanics, using operators and so on. But and then I think with Schrödinger showed that the two formalisms, the two ways of doing quantum mechanics, the matrix approach and the operator eigenfunction approach, this way or this way, were equivalent. And you see the equivalence here. That's pretty easy, right? Here's your operator and here's your matrix, and the conversion, if you like, between the two is pretty easy. Okay, so the algebra between the two approaches are equivalent. Okay. Okay, let's just something saying here. You can use one or the other. Now, things get a bit more complicated leading into the next session. what happens when so if you're using the operator Hermitian operator approach here with eigenfunctions, when you're talking angular momentum, your eigenfunctions become, if you remember, what was the term? Spherical harmonics. And spherical harmonics have two parameters, like they have L and M, right? So if you're using the operator and those spherical harmonics are the eigenfunctions to the two angular momentum operators. Remember, L squared and LZ. Okay. So your wave functions here, when you're talking in the context of angular momentum, and this operator here is one of your angular momentum operators, like L squared or LZ. Okay, here. And then these eigenfunctions here are now spherical harmonics with two parameters each, right? So you might have the spherical harmonic here where its two parameters are L and M, and you have a different spherical harmonic here where its two parameters are L dashed and M dashed. So this whole integral now is a function of four parameters. Four parameters. Now, see here, you know, this is one element of a square matrix, right? So with two parameters. So now with spherical harmonics, we've got like two parameters and we've got four parameters in this integral. So how do you interpret that as a matrix? Right? It's as though you have a matrix of matrices, meaning every element of the matrix is itself a matrix, if you see where I'm heading. So if each element of a matrix is a matrix, so a matrix of matrices, then that's where you could get your four terms, you know, your four parameters. All right. Well, I'm leading into this idea where you have four parameters, and I'll talk more in the next session about representations, because you can well, perhaps I'll stop there, otherwise steal my thunder for the next session. But I'm heading towards talking about representations of operators. I'll explain what that means next session.